second session. Okay, sorry. Yeah, good morning, everyone. Welcome to this fourth day, second session on behalf of Wilson College Physics Department and Indian Association of Physics Teachers, Mumbai Sub-Regional Council. We welcome Mr. Mahesh Patil, the speaker for the second session of this day. Mr. Mahesh Patil is a science graduate. As a profession, he works with Motilal Oswal Wealth Management. So we can see that he is working as a professional in different fields, but he continues to explore his passion in the field as an amateur. Now, what many term it as citizen science. Like earlier, we had Shishir Deshmukh talking about how the asteroid mapping is done using occultation methods. He was also trained in commerce, but he has developed this as a hobby. Okay, and hobby needs to be developed. So that was the idea that we were looking at. Mr. Mahesh Patil has been working on impact craters, ultra high pressure minerals and tektites for 7 years. He has presented the work in forums like Japanese Geophysics Union, American Geophysics Union, and Indian Geophysical Union. He has published 4 papers on the subject, got guidance from well-known scientists like Dr. Narendra Bhandari, ex-chairman of PRL, Ahmedabad, and Professor Mayank Wahiya from TIFR, and many others. He recently also received third prize for his presentation on his team's work from Bharatiya Vigyan Sammelan at Ahmedabad just last week. So we welcome Mr. Mahesh Patil for this session. Sir, it's yours.
Thank you, sir. Thanks all of you for giving this wonderful opportunity. Before we start, as sir has given you a background, this is my hobby. So whatever I'm presenting is a hypothesis. It is not proven yet, but yeah, we have made some substantial progress. Whatever I know about this, I'll try to share. There will be many questions which may remain unanswered. Okay, on that I'll keep working. Okay. So this is more, I want this to be more of an interactive on one-on-one discussion rather than a talk from somebody who know everything. Okay. So I'm also a learner like you. Second, we'll start with basics. I'm sure many of you will know about impact, nothing new about it. But still to have everyone on a same page and to make it little interesting, we will try with some basic concepts. In a very common terms, we'll try to explain and then we'll go to the actual fact or actual presentation. Okay. So the moon, this is our first introduction to night sky. This is what raised our inquisitiveness to know what is beyond Earth. Okay, we are all of us are excited. As we grow, our fantasies along with this celestial body grows. Okay, so we have a lot of dreams associated with this body. But as we go little closer, we realize it's scary. By the way, I'm talking about moon only, nothing else. Keep that in mind. So obvious the question is that what caused this? Now, any kind of damage is caused by close relatives. So our close celestial relatives called asteroids and comets are responsible for whatever you have seen on moon, the scary things on moon. So asteroids, you can classify them as our close door neighbors or our immediate relatives. We can easily identify them. They are of stony or metallic in nature or a mix of stone and metal. So they are something like us. We can easily make out metal asteroids will be heavy. They are like people having some social status. So they will look more heavy. Comets are a little different. They are more of elusive bodies. So they are more like a distant relative coming from very deep areas of our space, maybe from Oort cloud or Kuiper belt. And they typically behave not like close relative, like a distant relative or like in-laws, okay, to simplify the matter. Typically, whenever they are coming, there is a lot of aura. And when they come, they release a lot of gas. So you keep wondering who are they exactly. Okay. And whenever they leave you, they leave you with a lot of trails for the discussions. So we'll talk about these comets today in some more detail. Okay. So comets, they can be largely classified into long period comet and short period comet. So long period, like we classify people, whether they are residents or non-residents, scientists classify comets, whoever comes back to sun, depending upon their orbit period within, after 200 years, they are considered as long period comet, and their orbital period can go up to thousands of years. Okay. So they are very rare visitors. If you get to see one in your one lifetime, then your many generations will not see that comet again. That's the kind of behavior they have. And second are short period comets. They keep revolving within our inner interplanetary system. So they keep visiting us frequently. The classic example is Halley comet, who keeps visiting us after every 70 years. There are some comets who keep visiting at regular interval of 6, 7 years. So they keep revolving around orbits of Jupiter, Neptune, and between Sun. They keep revolving. That's the reason they are called short period comets. So their behavior is like also changes because of this. Because when you are moving around in inner interplanetary system, you are bound to be affected by various gravity fields of strong planets like Jupiter, Saturn, Neptune. And when you go close to Sun, apart from Sun's gravity, they also face radiation. So they pay the cost of staying in this inner interplanetary system, and eventually they tend to disintegrate. So this has been observed, not necessarily every short period comet will disintegrate, but this has been observed in many cases. Okay, eventually they pay the price for whatever they are interfering. Some of them, even after disintegration, can be dangerous. Okay. A classic example, when I was in my college days, this is what I was looking at. So during 1992, Schumacher, I'll just give you a small introduction to guys who want to know about this field. Schumacher is a person who's not only found this particular cometary event, but he's the guy who fought for impact craters when everybody was saying craters are on moon are result of a volcanic activity. He stood his ground saying that these are effects of or impacts of asteroids and comets. And during Apollo mission, his finding was proven. This man lost his life in a car accident in Australia during his field visit for impact crater. So we must remember him. If you get a chance to read about him, do read about him. If he would have been alive, he would have contributed a much more. But yeah, during 1992, he discovered this disintegrated comet called later known as Comet Schumacher, along with his colleague Levy. So Schumacher-Levy 9. This comet disintegrated into 21 pieces. It was a spectacular thing to watch. And then they realized that it's on a collision course with Jupiter. So whole world was wondering what is going to happen now. All the observatories, whether it is NASA, whether it is European Space Agency, Japanese guys, everybody was trying to note about this event. Let's see what happens to Jupiter. And it was a spectacular event. In 1994, over a period of few weeks, these fragments kept impacting Jupiter's surface. On the right, if you see infrared image of Jupiter, you will find these fireball kind of things that are coming up. On the left, we can see the marks which are left on Jupiter. Just to understand the magnitude of this event, this impact occurred. The plumes that they came out of Jupiter's surface rose to 3,000 kilometers in the atmosphere of Jupiter. So imagine a case, something like this happening to our planet. A plume of 3,000 kilometers rising above Earth's surface. It will be a horrible scene to watch. I'm sure none of us will be alive by that time because this will make sure none of us is present. Okay. So these are the bodies who can actually create some disaster. All of us know impacts like this have wiped out dinosaurs from our planet. So these impacts are not necessarily only limited to other planets only, even like or only to moon and other planets. Even we are target of these bodies. Luckily, our mama Earth protects us. Our atmosphere is a big shield. So many such small particles who try to enter. If you look at a night sky, you will find many streaks of fire crossing through the night sky. So these are small dust particles. There are also small other stones which are hurled towards us. But most of it is taken care by atmosphere. So most of them, they burn in their journey, and they eventually do some light show sometime. If they burst near Earth, then you will hear some sound also. So it's a light and sound show, but eventually they fragment down as a Earth, and you may find meteorites on Earth strewn over a small area. This is the map which shows how, or this is the picture how these bodies behave, but not necessary. Atmosphere or mom can protect us every time. Big boys are bad boys. They can't be stopped by atmosphere. So in the recent past also, we have faced few such events. And if you get a chance, do look at these videos or these details. They are available. They are very interesting subjects. One is technicality of subject. Second is experiencing something like this. So in 2013, I'm sure most of you may be in school, because I believe right now you're in college. So nearly 10 years back, you were in your primary schools. So during that time, one meteor entered over Russian skies at Chernobylskaya in 2013. Luckily, we have all the video shootings or video footages available of this particular event. And during this event, a bright light was observed in the sky. You will feel as if there is a sun. This small fellow blasted in the mid-air only, but still 3,000 people were injured simply by the shock wave. Similarly, in 1908, we have faced the Goose Sky event. Do read about this event. It's a most elusive event. It was considered as a very lucky escape for Earth, wherein it fell at a not it didn't impacted, but yeah, it went for a airburst very close to the ground in a remote place of Siberia. Luckily, there was no population, but still nearly 2,000 square kilometer of area was flattened in a matter of minute. The shock wave was experienced nearly 80 kilometers away. So people who were 80 kilometers away fell from their chair. They felt the heat of this particular impact. It occurred at Russia, but seismic meters in even in Germany recorded the seismic waves. So it's a very elusive impact that we know. It was a lucky escape for us and a reminder that you are no exception. Uh, so if we look at available record of our planet as of 2017, we have some 190 confirmed impact craters. But when we look at moon and other planets, especially terrestrial planets, this number sounds nothing. One of the reason most of our surface is water, nearly 70%. Thus, many impacts occur in sea. They are difficult to detect. Second, we are a live planet. Yeah, we have tectonic activity, plate tectonics are there, we have wind, we have vegetation. Most important, we have human activities. Because of this, many craters get obliterated. Second and most important criteria for calling it as a crater is the strict norms by geologists. Because for a subject of geology where you are working on a planet having a history of 4.5 billion years, this particular event which occur for few movements, tracking it down, this particular movement in a history of 4.5 billion years is like trying to find out a needle in the sea. It's very difficult job. And that's why the norms are very stringent. So typically you need to have a circular depression or a crater, what we generally call it as. That is considered as a strong sign of impact. But again, there you need to differentiate. Is it a volcanic crater or is it an impact crater? Then you need to look at various high pressure minerals which are available, which are formed because of this impact. Uh, because of the shock wave, there are certain signatures which are printed on stones that are called shattered cones or planar features. They need to be present. And in some of the cases, tektites are formed. So one of the reason why we have highlighted, that is one of the major clue that we are going to use to discuss today's subject. So what are tektites? Just to give you a brief idea, in the event of a larger impact, when dust is thrown out, I'm sure most of you would have seen some footages on a nuclear blast. So you have that ejecta cloud that goes, which form mushroom cloud. So that ejecta that is thrown out in the air, some of that impact melt from Earth goes out of atmosphere and they re-enter in the atmosphere by gravity. So in the re-entry process, they again start burning. Already it's impacted or melted or heated. While entry, again re-entry, again it start burning. Thus, it becomes a homogeneous glassy kind of object and it obtains aerodynamic shape. So right now, if you look at it, right now on display is dumbbell shape tektites or teardrop. There are also button shape, flange shape. There are various type of tektites that are formed. Now, these tektites are unambiguous evidence that there is an impact that has occurred in this particular region, and you need to track them, and it must be a very large impact or a bigger impact which threw material out of our atmosphere. So, typical formation of a crater, before we go in too much of a depth, most of the impacts occur at around 45-degree angle. Okay, so you get a circular depression. And probability of a low angle impact, that is less than 15 degree, is hardly 6.5. And a grazing impact, that is impact which is less than 10 degree, is hardly 0.75. This is what Schumacher arrived basis various calculations. So grazing impact can result into crater and ejecta distribution, that is distribution of tektites, which can be not only tektites, even other fields, which is very, very different. Okay? Thus, grazing impacts are very unique. I hope, in case if you have any doubt, please feel free to ask any questions. Don't wait, because one, we are talking about impact. In that, we are talking about a grazing impact. Okay, and thus I was trying to keep it simple. So if you have any doubt, please ask. Don't wait for end of session.
Okay. Is there, I mean, this calculation Schumacher had done about, most of the impacts happening at 45-degree angle and very few happening at grazing
Yeah,
angle. So,
yeah.
is there a kind of physical significance for, this part? Is it
See
just
the
that
yes.
major area, I mean, major cross section you find where it may be 45-degree, but the edges will be grazing and therefore that edges is very small. Is it only that, or is there any other kind of reasoning
So
behind
main is
this?
all about how the entry take place in Earth's atmosphere. It is something to do with where the objects are coming from, what is their trajectory, and at which angle they are entering into Earth. Because basis that, shape of the crater will be defined. Even if it is a 30-degree impact or a 15-degree impact, the circularity doesn't go. Only at this very, very grazing angle, we have shown some examples in the next few slides about how grazing impact appears on other planets. It also has implications on aftermaths of impact about how shockwave travels. Okay. So just to give you a simple example, since you have asked this question about this, it is like throwing stone in the water. In a normal circumstances, it will go down. But if you throw a stone at a very low angle, we see skimming in the stone. So if you go near water body and try to throw stone at a very low angle, stone bounce off the water. Now it's a typical peculiar behavior of a projectile, even in case of impacts. So fragmentation take place and they ricochet from the surface, creating some different scenarios. Okay, so Schumacher has written a detailed paper on this. It's a very complex calculation. Even this probability calculation they have done on various factors. Okay.
There is one question in the chat. How can a 45-degree angle will cause circular crater instead of elliptical? Hmm.
So there are various models. So obviously 45-degree angle is more or less a circular. If the angle becomes little lower, 30. So lunar, if you look at prima facie, you may feel this is the crater in the background is lunar. This impact has occurred somewhere around 30 to 40 degree. Now, if you try to draw perfect crater out of it, you will realize it's a little elliptical or elongated crater. It is not exactly circular crater. So obviously, it is not necessary every time it is perfect circle. But at 45 degree, yeah, circle is means overall crater is circular, and there are various models. If you want to test, go to ICEL. ICEL has a detailed working on these impact models. You will find even at 45 degree, the crater that you get, because the shock wave, the way in which when projectile touch down, the way in which energy is transferred is more or less circular. And that's the reason the crater that you get is more of a circular depression. Depending upon the size of the projectile, strata, various angles, some changes will occur. So some craters will come as a simple bowl-shaped crater. Some of them may have a mound in between. Some of them may have multi-ring. It all depends upon density of projectile, angle of projectile. There are many factors to it. It's a complex mechanism. But ICEL is a great model. If you want to understand, you can visit that model. You will come to know about how these craters are formed.
So can we say that the actual meteorite maybe just a few meters, but the crater is few hundred meters. So it's all the shock wave which is causing the crater. I mean,
100%, sir. It is
can we
mainly
just
the velocity which does maximum damage along
and
with the mass, obviously.
because for a given particular area, the shock wave speed will be same in all direction. It will be more or
Yes,
less circular. That
100%.
that is
That
what
will be more or less
okay.
circular. We are more precise, I think. As a, okay,
Okay.
fair. So one of the Australian tektite field. So now we'll come to the main subject. I just gave you background about this study and basics about this study. So right now we are discussing about Australasian tektites. If you look at the map behind, they are spread across entire Southeast Asia till Australia, and even in Indian Ocean, some of their fragments have been reported from. So this is a known fact for more than 100 years. So tektites are spread over 10% of Earth. Now these tektites, it's a very unique field because there are two type of tektites that you get. One is heterogeneous Myeongdong tektites, and second is homogeneous melt. So melt is what I explained you. When the ejecta is thrown out of atmosphere, it eventually melt down and come back. And again, during re-entry, again it burns. So it becomes a glassy material, and that's how they are homogeneous. Heterogeneous one, they have not traveled beyond atmosphere. They have stayed within the atmosphere. So whatever initial melting has happened with them, that is the only melting, and that's how they have remained heterogeneous. And their weight is on the higher side in case of Myeongdong. And that's the reason assumption is that if Myeongdongs are found, impact must be in nearby locality. So the whole search for impact is going on in the Indochina region, mainly towards Southeast Asia. So Vietnam, Laos, they have tried to find out many sites. But
There is
barring tech,
a question
yeah,
uh, that you mentioned about ICEL model.
mhm.
So how do you spell that?
I small I SALE. I have mentioned that in the next slide so that
Okay,
you will come
okay,
to know.
fine. Yeah.
Okay. While designing how this could be, we have tried to show that. Okay.
And there is another question. What is the chemical composition of a tektite?
So tektite is typically most of the composition is an impact melt. So on impact, when the velocity, the shock wave is transferred, the immediate area, there is a melt. So most of the rock will melt. Not only rock will melt, even projectile will melt. So the tektite, majority of composition will be of a impact site, and some portion of it will have projectile, which is as an inclusion. And eventually this melt will go up in the sky and fall down. So there will be burning. So tektite, sometimes you may find volatiles in that. Sometimes you may find rare minerals in that. So tektites are used to find out one, the target location, and second, the probable projectile that has caused it. Is that sufficient?
Okay, so basically you can say that whatever is the local rock that will
Yeah, local rock that
become
is
glass
melted.
and it is called tektite.
So local glass that is melted, and local, generally most of the earth has quartz. So eventually that turn into a glass. Okay? And that's how it is a glassy material because of burning. And signature will be of a terrestrial rock where impact has taken place.
Thank you, sir.
Okay.
No more right now questions in the chat.
Okay, great. So now homogeneous melted tektites, but Myeongdong are heterogeneous. So assumption is they have not traveled beyond atmosphere. Second, impact must be in the area of Laos, Vietnam, or Cambodia. That has been the assumption. But despite of that, we have not got a single signature. And this is a very recent impact in geological terms. Nearly 7 lakh year ago, this has happened. Now, in geological terms, 7 lakh is a very recent one. If you look at the impacts which wiped out dinosaur, they happened many million years back. Australia has many such signatures, very old impacts, still they are alive. So you get reasonably well-preserved craters. Here, not only we are getting craters, we are not getting any high-pressure minerals or no other signature except tektites. So initially people thought this must be airburst. But in case of airburst, you can't have tektites because where the impact melting has happened, ground melting has not taken place if it's a airburst, and it cannot go up. So there are many dilemmas which are around this. Okay. So the expected impact site, the minimum size of crater for such a large ejecta field should be 70 kilometers, 70 to 100 kilometers. Okay. So the mystery is where is crater? Right now we have all the technologies. We have satellites, we have remote sensing, we have each and every technology available apart from field investigation, but nothing has been reported till date. So what is the problem? Problem? Mainly search is focused about Vietnam, Cambodia. When we know it's a tektite field, so it is not a circular field. I'll just go to next slide. So this is what happens. Take and then will go back to earlier side. So in case of 45-degree impact, as I told you, most of the ejecta will be circular and in the crater will be more or less in the center. Okay. But in case of highly oblique impact, ejecta will be more or less within a narrow fan and ejecta will be distributed in the direction of impact. So wherever projectile is coming from, in the same direction ejecta will be thrown out. Not only that, as I told you, stone rebounds from the surface of water at a particular angle you throw a stone at. Similarly, in this case, generally, in case of normal impact, what shock wave passes through ground, same shock wave also melts the projectile. In this case, projectile is not melting completely. So Skulls has done a detailed working on this using a impact crater on the Mars, and basis that only we are doing this entire study. So in this case, projectile doesn't melt, rather it ricochets, and some of the projectile fragments keep traveling in the same direction at more or less similar velocities, which are equivalent to initial velocities. And thus, it is a strewn field which is concentrated within a narrow fan. Second, it is a mix of two type of tektites. One is projectile fragments, and second is the impact melt. So now, if we look at the problem with this, we are trying to find the source crater only where we are finding larger tektites, assuming they are nothing but impact melt. So these tektites may not be impact melt, they may be fragments from a projectile. So crater can be little further from where we are trying to search. Second is a grazing impact factor, because since the grazing impact possibility is so low, people have not studied grazing impact in detail. Schumacher was studying it in detail. Skulls had studied in detail, but not too many people have studied or focused on this particular kind of distribution. So when we try to search for craters, most of the scientists believe that it has to be circular. And there comes the problem, because we are not getting any circular structure even today. Okay. And projectile ricocheting somewhere down the line we have ignored is our assumption. This is my assumption. This is not a proven hypothesis. Yeah, we have certain data points to support this. So this is what we just explained to you right now. So this is the way impact in the event of highly oblique impact or a grazing impact at less than 10-degree angle. This is the way ejecta distribution is taking place. So, as I discussed, Skulls has done a detailed study basis on his work on Martian craters. Okay. This ejecta is more or less is in the downrange axis of the impact. Okay. At early stage of highly oblique impact, failed fragments means ricocheted fragments of projectile result into sibling impact. So some of these fragments travel down in the same direction and also create second impact. So then that side should have sibling impacts, and some travel down the range ejecta at the speed comparable to initial velocity, and that's how they form fragments of projectile which are spread across a larger region. So this is what we have explained in the, this is what Skulls have said. We have tried to simplify it. These are very technical terms that they have used. Okay, so I don't want to create too much of a confusion. Simply what he's trying to say or what he has designed is this. Okay. Now, if you look at Asian tektites distribution, now Asian tektites, right now, Australia also there are there, but right now we are focused only on Asia to simplify. Most of them are in a narrow fan. Again, it's a mix of homogeneous and heterogeneous tektites. Myeongdong have certain volatiles which are found in it, which are difficult to justify. Only, and that's how people thought these are fragments of cometary body, because comets have volatiles. So Myeongdong is a kind of a question mark when it comes to tektites, but because Myeongdong type of tektites are not found anywhere else. There are more than 10 strewn fields on tektites, various other strewn fields, but none of them are Myeongdong kind of a tektite. So this requires some detailed study. Second, more important, tektites are also reported from Myanmar and Tibet. Now, typically, fortunately, unfortunately, unless and until some European agency has verified it, it is not considered as occurrence. That was the way in which used to be in past. So Tibet, people were freely showing tektites, but nobody studied it. China is also very conservative about studying all these things for some of their, maybe some strange reason China doesn't study these tektites at all. Myanmar, there is a Professor Gangadhar from our own country who was there in, I believe, Vietnam. During that, he found these tektites. He has reported them, but nobody has taken that subject seriously. So if we are getting tektites in Tibet and Myanmar, second thing, some of the tektites have inclusions like lithium, boron, kyanite. These minerals are not present in Southeast Asia, but Tibet had some source. So we are of the opinion that Tibet needs to be evaluated. Now, generally basis this assumption, things are not going to work. Obviously, we need, I just described whatever we discussed basis the map. Okay. So one question that may come before we go to other substantiating evidences, can now Myeongdong kind of a heavy tektite travel such a large distance? Okay, so there are calculators available to calculate the trajectory. We have taken various probabilities. So altitude of Tibet is 4,000 meters. It is called as rooftop of the world. Altitude of Southeast Asia near China Sea, where tektites are found. Right now, we are assuming by and large it's zero, or it's not a very high altitude area. It's at a sea level. Some of mountains are there, but tektites are found everywhere, including near the sea face also, or rather in the sea also. Okay. So if we evaluate the distance traveled by these fragments, okay, if it's a projectile, if it goes out of atmosphere, then yeah, it can travel much longer distances. It all depends when it falls back, okay, because Earth is also rotating. But if Myeongdong is traveling with the initial impact velocity, they are ricocheted fragments, then they are not getting that advantage. They need to travel on their own. Okay. So if we assume they impact occurred at say 7.5 degrees, and the velocity of projectile was 5, 7, or 10. These are the three assumptions we have taken. Then they can travel distance anywhere between 500 kilometers to nearly 3,500 kilometers. For this, Omni calculator is available. If you want to use that. Any projectile motion that you want to calculate, I'm sure you are a student, so you will go through formulas. I have simply used the available freeware. We have used it on a couple of other softwares also, which are available to calculate the trajectory calculations. We have got similar results. There is no doubt about that. However, a detailed modeling, we are looking for association. If somebody can work with us, we are more than happy. So this is the calculation which suggests that Myeongdong can travel. There is no need to assume that Myeongdong have not traveled too much. If these are ricocheted fragments of projectile, they can travel. That's the assumption that has been made. So which region we are talking? So this is the region that we are talking. Now there is no circular depression, but there are multiple lakes which are in a particular fashion. That is what is raising doubt. And these lakes are not only we are assuming because it's a smoking zone. It's a smoking gun rather. Because if you look at Tibet, most of their mining happen in this area. They have been getting strange minerals in this area which are not found anywhere else in the world. And there are specific minerals related to impact which are reported from this region. So we'll talk about those specific minerals and why they are saying they are not impact mineral, and they are simply trying to justify them as a mantle origin. That theory is very, very difficult. And when we approached China, they were very reluctant. They said, if we need you, we will let you know. So generally, they don't allow anybody to work in this region. Their commercial interest is of very high order. So there are question marks on this study. And these are the questions which we have tried to raise. So for last, I think more than 20 years or 25 years, China is aware that they are getting certain minerals. So one of the biggest evidence of impact is cosite after stishovite. So as we were talking, when impact occurs, there is an energy transfer that happens on a ground, and when the shock wave is passing through, quartz particles, they turn into various kind of glass forms. So a tough glass called cosite immediately, and then it results into cosite, which is formed after stishovite. So these are the glasses which are undisputed evidence that there is an impact that has occurred. So if you get cosite after stishovite, 90% you have cleared the test of impact is what scientists believe. These cosites after stishovites are reported along with microdiamonds. Now, microdiamond is a second signature of impact. There are other signs of impact like high pressure form of titanium dioxide. Now, titanium dioxide is available everywhere on the earth, but TiO2 is very rare. You need a very high pressure. There are also certain nitrides which are formed on which we have done some further arguments. One of them is cubic boron nitride. Now, cubic boron nitride we discovered because somebody told, during my initial days, somebody said if you want to prove impact, then you will have to look at Lonsdaleite. Lonsdaleite has a hexagonal cubical structure and it's a diamond which cannot be found otherwise. So when I was looking for this, I came to know that there's cubic boron nitride, which is nothing but similar to Lonsdaleite. So when I approach people, they say, no, just because structure is similar, it cannot be associated. So I said, let me study. So I'll show you how cubic boron nitride is found in natural environment. It is not possible to find it. Same is the case with boron carbide. Now, all these minerals, they need temperature of 1300 degrees centigrade or pressure of 10 GPa. Now, pressure of 10 GPa is there 300 kilometers beneath Earth, and 1300 degree doesn't come on surface naturally. The area which is found is ophiolite. So ophiolite is nothing but uh, part of a sea which has raised because of the tectonics, plate tectonics. So it's a phenomenon that occurs at 30 kilometer at max. So there are contradictions in that. There are many contradictions. Most important, if you want cubic boron nitride for mantle origin, you need to know source of boron. Boron is not a metal mineral. Boron is not there in the metal of Earth. It is found in traces mainly as a concentrated form on the field as borax or boric acid. And Tibet Lake region is known for borax. So the raw material required is available on the surface. Why are you trying to look at metal? These were our questions. But impact provides a simple explanation, that is our assumption, and especially a cometary impact. Comets are consisting of water, ammonia, carbon monoxide, and other complex elements, wherein Tibet has borax, TiO2, SiO2, kyanite, all these minerals are available. Impact definitely creates this temperature pressure condition of 1300 to a degree centigrade with pressures in excess of 10 GPa or going up to 15 GPa as well. So this impact occurs at 1300 degrees centigrade and greater than 10 GPa pressure. Borax reacts with ammonia of comet, forming cubic boron nitride. That's the simplest explanation available. Along with that, they are also source. Comets are also source for carbon monoxide. That result into formation of boron carbide. Both these minerals cannot occur in natural phase. I have checked with PRL, I have checked with various agencies. People who don't believe or still challenge for impact craters in Tibet, they also say these two minerals can be defended in the natural environment. So these are our strongholds. Apart from that, osbornite is found. Osbornite is a rare thing. But formation process of this osbornite is by nitridation. It is not by natural. I'll not go into much of a technicality. If you guys are interested, you can read my paper, ultra high pressure nitrides and microdiamonds from Tibet. If you want, I can share the links with Professor Saab. You can take it. So TiO2, cosite, stishovite are any which way easily explained in the event of impact. And all these minerals are found in assemblage. So mantle origin doesn't confirm their assemblage. That is very rare. It is very difficult to understand. But impact can easily confirm their why they are found in assemblage along with microdiamonds. So the question is that okay, we have tektites, we have high pressure minerals. There are many clues about it. But where are the craters? There are no craters in Tibet. There are no circular depressions in Tibet. Okay. Right now, we haven't been able to prove anything as a crater. To prove something as a crater, you need to visit that place. China is not allowing anything to be done in that region. We are trying to figure out various sources. If any one of you have something, some connect, more than happy to associate. So, since there are no circular depressions, most of them are ignoring. So, there is no need to investigate. Okay. Crater must be somewhere else. But we generally say the tektite field is such that is at 10 degrees. So what about angle of impact? We must evaluate what kind of angle was there for this tektite formation. So can that angle of impact give you a circular depression? The answer is definitely no. Okay. So the question is how oblique impact craters look like. So these are the ICEL models that I was talking about. I have written the name, how ICEL can be checked. Small I, SALE. Okay. They are difficult people to access, but yeah, they have done some good work on angle of impact and various other factors. So at 10 degree, you will find elliptical or oval shaped crater, and still you will find some kind of a drag in the tail of an impact crater. At 5 degree, it becomes a very elongated kind of a crater. So there are some craters on the Martian surface. These are the images clicked by NASA. My mistake, I didn't give them image credit for that. Uh, but these are the images clicked by NASA on the Mars, and these are proven oblique impact craters. So ICEL model, and if you look at these craters, you will find there is a lot of similarity in that. So ICEL is not incorrect. These models are more or less in line with what is found on Mars and even on Moon in some cases. So you can study oblique impact craters. There are many images available on oblique impact craters. Those craters can be little weird than what we know for a standard impact crater. But since on Earth probability is low, nobody is studying them so seriously. I think after skulls, nobody has worked on oblique impact. Schumacher was a believer, but unfortunately passed away in an accident. And after that, work around crater has been limited to whatever we worked initially during Apollo mission. Our understanding has been limited to that. So now if we look at some of the Tibet lakes, they have some interesting features. So we'll start with the third. So if you look at the right Orcus Patera, I have taken second angle of Orcus Patera and I have shown a couple of lakes in Tibet. So these are twin lakes in Tibet. Now they have some similar structure. There are at least 8 to 10 lakes in Tibet, which are 50 kilometer or 15 kilometer. If you look at length by, and if you look at the left-hand side of these lakes, you will find a ridge. So we think that somewhere down the line, these may be possible craters. And surprisingly, near all these lakes, China is doing heavy mining activity. So wherever lake is getting discharged, they have done their placer deposits. Placer deposits are the mining technique which are used near the water discharge points, because you need not dig anything, you get things naturally with you. So all these lakes, we have spotted all those mining activities. If you look at the second picture, the central picture, there are concentric rings which are there in front of this lake. Now these rings are typically observed near crater also. So these are smoking guns. We don't have any conclusive evidence to say what we are saying is 100% correct. Unless and until you do field investigation, you can't say. So these are proposed craters. Now if these are craters, then ricocheted fragments, as we said, should have sibling craters. So we have found few things which appears like a sibling craters. But again, unless and until, and they are in direction, they are in sync with the parent craters. Okay. So, but right now, whatever is there is based on images, various satellite images or remote sensing. No crater can be proved without field investigation. So our study currently on craters has limitations. Our minerals, high pressure minerals, is the strongest point, which even Chinese haven't been able to counter us. We have been allowed to present our case. Our tektites, Indian Geophysical allowed us to publish our paper on tektites. So those are strong points, but yeah, the currently missing link is confirmation of impact crater, and which is right now a limitation, because without field investigation, that is not possible. So right now we are simply concluding on the basis of available data on Myeongdong tektites from Australasian Stune and other Asian tektites. It appears that the Stune field is a mix of a layered tektites known as Myeongdong and splash form tektites, which are Asian tektites. The distribution in narrow fan is consistent with the study of oblique impact on a hell crater. So the crater which is used as a reference point by skulls for study on impact crater is hell crater. And if somebody is very interested, they can go through this paper of skulls. It's a very beautiful paper. When I came, I'll just tell you an interesting story. For many years, I was wondering why tektites have traveled so much. I was not able to understand. Okay, because I had high pressure minerals, I had tektites, but I was not aware how they have traveled. So one day I was traveling with my kids for a picnic at a Tansa lake, and I was showing my kids how we used to throw stones in the water. And when I threw one stone and it jumped, she said, "Dada, how you did it?" So I said, "No, if you throw at this angle, it means ऐसा low फेंकोगे तो जाएगा, direct फेंकोगे तो डूबेगा." And that was an eye opener for me. What am I talking about, Ola? This is what may be the case. And that's how I came to know about angle of impact and its effect on projectile. I searched on net, and that's how I got this paper. I got multiple papers. What impressed me a lot was skulls. So keep your minds active, keep it open. You never know what things will come to your mind, and those ideas can help you a lot. So coming back to subject, inclusion like FENIS. So this is called Shenzhungite. I've not gone into all these technical details because maybe a little complicated. Now Shenzhungite is found in comets and volatiles like chlorine and bromine found in Myeongdong, okay, along with presence of cosite. So we have explained in our paper how they can be inclusion of Myeongdong, because these are not the things which are found in tektites. Myeongdong have this. FENIS can't be a terrestrial composition. So FENIS is found in comets. So this may be a cometary fragment. That's our argument. Okay. So this may be a ricocheted fragment of a projectile-like comet. Thus, Myeongdong and other Asian tektites may be result of oblique impact at an angle of 5 to 10 degree to horizontal surface. Abundance of lithium and boron in Myeongdong restrict the search area, because if they have lithium and boron, what is the source for it? So that area get restricted to more or less regions which are known for this richness, and Tibet is one of the regions known for lithium and boron deposits. Presence of cosites and stishovite and other ultra high pressure minerals in Tibet Lake region, okay, with unconfirmed report of tektites found in the region, support the argument of impact in Tibet. The basic trajectory calculations are in line with the current geological spread of Myeongdong. Hence, we suggest that oblique impact in Tibet may have been responsible for tektites reported from Asia. But yes, unless and until I prove the crater, this will remain hypothesis. So don't say that Tibet is the impact right now. And I'm saying it's a hypothesis, not a confirmed impact. So I've covered my subject. I'm sure you will have some questions. So I've tried to keep some 10-15 minutes for that. Happy to answer if you have any doubts.
Okay. How did you start working on this project? From where did you start,
When did I
thinking
start?
about data? You mentioned about this skimming thing to get an idea, but how did you decide to even work with uh, these kind of things?
So it's a strange mystery which even I'm not able to address. Okay. One day I was watching some program on Discovery, and that's the point where I came across the concept that comets have played a major role in shaping of our planet. So before we go to answer your question, these impacts are not bad. They also give many things to us. They have given us rare elements that are found on our planet. They may have given us the very nitrogen that we breathe. That is a big question mark. These objects have contributed that. They have contributed water, and they might have brought life to the earth. So one of the story that was discussed on Discovery, how comets have played role in getting water to our planet. And that struck me with certain ancient literatures which talk about some certain events. Okay. And those events were in certain areas. Right now, not go into that discussion because it's a very unique subject where you work with. Even China had certain stories that impact took place, or a celestial body came from heaven. It was an icy object. Even India had certain stories. I'll not go into story because right now our forum is more of a scientific forum, and I generally don't like to mix two subjects. But yeah, this was recorded. And I said, if this story is correct, there should be evidence of impact. It took nearly 3 to 4 months for me to find this location. And after finding this location, when I was trying to say this is the site, people said you need to have. And that's the time when I got in touch with Mayank Vaiya, Professor Bandari, Professor Narlikar. They said, as a concept, it is possible, but first you need to have evidences. And that's how I started gathering these evidences. Then there were challenges. When I wrote my first paper, I was ridiculed very, very badly by some of the fellows. Rather, the competition is the best teacher that you can get, because their hard words made me work more harder to prove my findings. Still, I'm not done. It will take a lot of time. But yeah, it was a coincidence. That's what I can say. But at the same time, science is science. There is no question of involving any literature when it comes to scientific thing. You need to have hard ground evidence. Then only you talk. Else, keep mum.
There is a question in the chat. but I will ask Akash Vedi to speak because then he will be better able to answer, ask this.
Yeah.
Sir, my question was regarding the atmosphere density because as sir explained about tectides that they means they jump off like scheme over the atmosphere na
They don't
for
skim
few
over
times.
atmosphere. No.
Hmm?
If I have explained it incorrectly, let me. Tectides don't skim over. Okay. What happens at the time of impact? The velocity of projectile can be anywhere in the range of 10 kilometer going up to 50-60 kilometer per second. That's a humongous velocity. So if you calculate in per hour, it is like a large rock, say 100 meter, 200 meter boulder traveling at a speed of 1 lakh 80, 1 lakh 90,000 kilometer per hour, impacting the earth. Now that is a humongous speed. Energy released during these events can be much bigger than many nuclear bombs. So just to tell you, lunar crater, if you look at energy released during lunar is estimated around 600 to 800 Hiroshima nuclear explosions. That is 6 megaton to 8 megatons. Now with this energy, the ground melts. Not only ground melts, the ejecta mushroom cloud is formed, and this cloud or this ejecta can be thrown out of our atmosphere. So they are thrown out by force, but eventually they are not able to escape gravity. Then they fall back because of the gravity on ground, and during the re-entry they melt. So tectides don't skim. I am saying when projectile impact at a very low angle, projectile may ricochet, and some of the ricocheted fragments may skim from the surface, or that is called ricocheting of projectile fragments. So there are two different things: melted tectites and what we are talking about, muon now. Our assumption is they are ricocheted fragments of projectile. Continue, discuss, don't hesitate. I may be wrong, Mitch, or I may not have understood you. So
No,
please.
sir. Actually, I was curious about because as you said, like my it might take some time for a tectites to reach back to the Earth, na? Like due
Yes,
to
it
the
takes time.
atmospheric density of the
Yes,
planet must be depending on it.
yes,
So for that scenario, I just consider the Venus planet because it has a densest uh atmosphere, like you medium.
yeah,
So how about that scenario? Like over there might be so many tectites in the atmosphere, na?
yeah, definitely. So if you want to understand the strewn fields, there are some classic photographs available by NASA, rather hell crater that I explained you. They have taken pictures of the entire strewn field of hell crater. That's the great work done by Skulls. There they have explained the entire distribution, how it happens on other planets. So obviously density will play a role. In case of higher density, the burning scenario may be very high. So eventually they may melt completely, forming very tiny particles. I don't know how it will happen. I'm not an exact expert on how Venus will behave or Venus tectites will happen. But yes, in Mars, these ejecta distributions have been studied in detail. If you are really keen, study paper of Skulls on, because he has given the actual photographs, how sibling craters are formed by these ecochated fragments, how ejecta has been distributed. They have done the entire calculation. So yeah, it's a complex scenario. Many tectites are there in the atmosphere, and that's how they travel long, because Earth is rotating. Earth is not stopping. They have gone out of atmosphere. Earth is still rotating. So when they come back or they fall back, they may fall at a much larger distance than the impact site. And that's why tracing tectites back to the original crater is a complicated subject. And that's where you depend upon composition of tectites and the target rock.
Uh, Sir, can you share some journals which may help students to read articles on such kind of models, or more
Uh,
information where, because many students wish to take for higher studies may choose these kind of projects, and they need to write SOPs, and many times they are not aware of, because they are not read the research paper. So
yeah.
can you suggest some kind of
Sir, two, three things I will definitely suggest. There are many papers or many journals who talk about it, but people who have simply explained this subject very beautifully is there is a work on impact rating by J. Melosh. I'll just check. Yeah, Melosh only. I forgot the name of that book. It's a brilliant book. Please refer that book. They have explained impact cratering in detail in a very nice, simple manner. It's not about complicated terminologies. They have explained each and every aspect of how impact takes place, what is the role of composition of various projectile, what is the role of target rock, how energy play means velocity plays a role in impact cratering, various type of craters, how they are formed, whether it is bowl shape, whether it is flat floored, multi-ring craters. They have explained that. They have explained about shattered cones, how to differentiate that. So I think I'll share you that book, sir. With I have that soft copy of that book. I'll share that. If you want, share that with students. Anybody working on impact craters should study his work. It will make your fundamentals clear. I keep reading it. Not necessarily I've understood in totality, but it's a very interesting book, which I'll recommend. This was recommended to me by Dr. Mishra. He's a great guy who has been assisting me. This was also recommended by Dr. Bandari. So this is a book which I will say is a basic.
Impact cratering geological process, right?
Yeah,
That's the title.
it is an impact crater. I'll send the exact book. I don't want to be because I forget it. I keep opening and reading it. It's a soft copy.
Okay.
So I'll
Okay.
send it to you. I have in my home PC. Second, my submission is that just to keep your interest alive, do visit Lunar site. It's a wonderful site to watch. If you have
Yes.
holidays going on, it's a 2-day journey at max. You also have other places, but Lunar is a place that one should see because that is a crater near to us, and it's a very interesting site.
Yes, it is about 120 kilometer from Aurangabad or about
Yeah. About
90
100 kilometers
kilometer
from
from
Aurangabad.
Jalna.
Yeah,
Yeah.
yeah.
And I think the closest railway station is Partud.
Partur is the closest railway station, but not necessarily everyone will be comfortable with Partur, so you can continue traveling from Ahmedabad, Aurangabad, okay,
Okay.
because Partur is a very local village. If you are a backpacker, it's an ideal village. You stop there, take a rest, go to Lonar straight away. But if you want some good amenities and facilities, go to Aurangabad. From Aurangabad, you can hire a car, whichever way you are comfortable.
And in Lonar itself, there are places, no, where you can
Yeah, they
staying
have their
facilities are
yeah,
there.
they have
So,
their MTDC resort. That's a nice place, but I don't know. Bookings are generally full. When I tried, I didn't got it. So I stayed at Partur. I just wanted to make a 1 day. But it's an interesting site to watch. Do carry magnets, do carry various instruments, or you will find many anomalies. Do carry compass. Compass needle start shaking at many places. So you will realize what long-lasting impact. So if you look at stone, you will find that melting, what melting means, you can actually see it there on some of the stones. You can also try to find shattered cones. It's a beautiful sight.
sir, about I mean, coming back to again because you are pursuing this as a passion work
Yeah, it's my passion.
apart from your beyond your profession.
Yeah.
I mean, so how did you even you were interested in geology or astrophysics, or suddenly this particular kind of a problem has come?
Mm.
That reason I'm asking is there are people who could be seriously interested in different kind of studies, but the when parallelly reading other things as a part of general reading, suddenly they may get interested into the problem, and then how do you go about it? So if you can explain that.
So you are trying to means I'm little confused. So you are saying how I keep pursuing this is the
Yes,
question?
yes, yes. So, I mean, what is the kind of method that you're using to pursue this? Because there are various ways. I mean, people may just keep watching YouTube videos and uh, go nowhere out from
Okay.
that.
Yeah. Yeah.
And there are people like you who are seriously pursuing it into the more concrete work. So what is the difference? How do you
Difference, I'll say simply one thing. Well, when I came across this, I don't know what triggered, but I became crazy about it, to be very honest. At one point of time, my wife started asking me question, what the hell are you doing? Means, what is your job and what are you wasting your time on? So there are resistances that you come across when you are crazy. But yeah, first of all, keep experimenting. No harm in failing. First, don't get depressed by failures. You will not get success in initial attempt. Keep making mistakes and enjoy those mistakes. Learn from those mistakes. First, accept mistake. हाँ गलती हो गया, ऐसा कुछ नहीं है. You will not get success, especially if you are entering into field of research. Research is all about making mistakes, is my opinion or my experience. Second, talk to people who have really done work. These people are maybe a little difficult to approach. This may take time, but if you show your honesty and sincerity, they will help you. Even in today's world, I can tell you, without Dr. Bandari or without help of Professor Mayank Vaiya, I wouldn't have been able to do this. You may have difference of opinion at some times. If you believe in something, not because of your ego, but if because of rational, stick to it, but don't get into arguments. Is a important thing. If they have perspective, listen. Okay, they have their own perspective. Just because some points are not matching, not necessary you should say they are wrong. Don't be judgmental, because over a period of time you may change your opinion. Over a period of time they may change their opinion. So allow things to evolve. Keep reading and uh, keep enjoying whenever you get something which is new, because unless and until you enjoy your efforts, that continuity will not remain. So if somebody asks you to run without having any interest or passion, you will not be able to run. But if you are passionate, I know people who are at 60s, they are completing full marathon. So it has to come from within. It can't be forced on you. And you should be adaptive. You should be open. You should be open for failures, many failures. Then only success will come. Still, I get failures. Still, I get ridiculed. It hurts. It hurts you badly. But you need to then come back, come out of it. And rather than entering into argument, you need to work internally on your own work so that you don't give chance to people to say something. This is my thing, not necessarily it will apply to everyone. That's completely individual experience. But yeah, most important, you need to be passionate about whatever you're doing. Is that what I can tell you?
Thank you, sir.
Thank you, sir.
Right now, there are no questions in the chat. Okay, let me just, yeah. There is a good comment by Professor Rama Pandey, very inspiring words. Thanks, he said.
Thank you.
Yeah. So I take this opportunity to uh, thank Mr. Mahesh Patil for sharing his work and his passion, and I'm sure this will really help students to work towards the passion, because as a profession he is working in a different field, but when it comes to working, you can see that he has been working on this particular problem for 7 years now. Of course, he is working for 7 years because of his passion, but also because he's working it as very small part-time kind of a thing, because he full-time work is may not be able to focus on this. But you can also see that how passion can be developed. One has to pursue these things and keep reading, keep talking to people. So thank you, sir, for giving these inspiring words. Also, important suggestion for how to develop the passion in the field of science or anything. And thank you for being with us and giving your time for our participants. Thank you.
Thank you very much, sir, for giving opportunity to me. Again, I'm telling, I'm not an expert. I'm a student like you. So whatever I have said, if you have doubts, read more. I may be wrong in some aspects. This is a hypothesis, not proven one thing. But still, if you want to read my papers, you must read high pressure nitrides and grazing impact. I'll share those papers with sir. Those are papers which are well accepted by many renowned scientists. So you can enjoy that one.
Sure, sir.
Thank you, sir.
So, thank you, sir.
Thank you.
All participants, we will please fill the feedback link which I have put in the chat, and we shall meet for the next session at 4:30. Okay, see you by then.
Thank you, sir. Bye.
Bye.